So let's take a look at this problem together. It says that we have a wheel that has an angular velocity of 18 radians per second. And it's slowing down at a rate of 2 radians per second squared. And actually, I gave this a positive value, so if it's slowing down, I know my omega, my initial omega, and my angular acceleration have to be in opposite directions. If omega is positive, alpha has to be negative to get the slowing down part. By the time it stops, we want to know how much have we turned through. So what is our theta final? And I know that I'm going to just say that we're looking for really how much has it turned through. We're going to say that omega naught is equal to 0. We're just going to arbitrarily set wherever this point was on the edge. That's going to be our starting position of 0. We're going to figure out how many degrees or how many radians we turned through. So we'd really like an equation that relates the final with some initial cases. So we have one. We know that the final angle is equal to my initial angle plus omega naught t, should probably make these all knots, plus 1/2 alpha t squared. Well, I have this is theta final, this is what I want, is equal to omega naught t plus 1/2 alpha t squared. Well, this is great. I have omega naught, I have alpha, I want theta final, I don't have t. So I actually have to figure out what t is. I'm going to switch colors and we're going to solve for t. There's one bit of information we have not used, and that's our final omega is equal to 0 by the time it stops. That's my key to saying the omega final is equal to 0. So I have another equation that omega final is equal to omega initial plus alpha t. Or that omega final, or omega naught, because this guy is 0, omega naught is equal to, minus omega naught is equal to alpha t, or minus omega naught over alpha is equal to t. So I have this equation here, and I have that equation there, and I'm going to combine the two of them together. I'm going to slide this up a little bit. I'm going to rewrite this guy. So theta final is equal to omega naught times minus omega naught over alpha. Right, I'm just substituting in my value for t, plus 1/2 alpha times omega naught over alpha with a minus sign squared. My t squared, which goes there. So now I work through this problem and I find that I get minus omega naught squared over alpha plus 1/2 omega naught squared over alpha. I have an alpha there and 2 alphas down here, which equals minus 1/2 omega naught squared over alpha. So I plug in my values for this. I have minus 1/2. My omega naught is 18 radians per second quantity squared. And I put this over -2 radians per second squared. So my radians, one of my radians will cancel with one of my radians out. My second squared will cancel my second squared. I get the right value at the end for my unit, and when I work this out, I will see, I'm going to quickly do this, this is about 20, so about 400 over 4, so I'd say a little bit less than 100. So the only number that I have that's less than 100 is 81 radian. So this is equal to 81 radians per, or radians. So So not a hard problem, it just took us a little while to get there. We started off with our initial conditions. We tried to solve for a final theta. We were missing time, so like we did with our first kinematic equations for position and velocity and acceleration, we're going to do with our angular ones. We're going to solve the angular acceleration equation to get us time, plug the two equations together using substitution, and solve it in the end.